All right, so we will start section 3, chapter 3, which is about the waves. Uh, Section 1 and 2 basically defining simple harmonic motion, and section 3 is defining the waves because they are related. Waves also a kind of vibration, and simple harmonic motion also defines the motion of vibrating object. For that reason, we will use some information from section 1 and 2 to define the section 3, so which is about the waves. And first, we will talk about a little about the water waves. So introduction to the waves will be with water. So we will first define a still water. I mean, the surface is so flat, so there is no wavy surface. There is no disturbance. But this is a disturbed water. Let me start the animation. Maybe this is better this to see like this. So this is a disturbed water, and this is a still water. Right here, the surface is flat, but here, so surface is not flat, it is disturbed. Disturbance is traveling in this surface. How can you produce a disturbance? How can you disturb the surface of a water? So just you are going to drop a piece of rock, which is called a pebble, into the surface of water, and then you are going to produce a disturbance like this. So disturbance starts from the point where the pebble hits. So this is the point where the pebble hits and expands in all direction. As you see, it's starting to expand on the surface of water. And this disturbance, this traveling disturbance, is making this traveling outward in all directions on the surface, so making a circular pattern away from the original disturbance. So when you drop a rock onto the surface of the water, so then you disturb the water and disturbance start to expand on circular pattern from the original of the disturbance. And this traveling disturbance in physics given a name which is wave. So then we say that wave is a traveling disturbance. And uh, as disturbance is traveling, something very extraordinary, maybe not expected, is happening. As wave passes, or as a disturbance is traveling, objects or particles on the surface of water vibrate up and down, back and forth, and then draw vertical circles, but they do not displace. Only they stay in their place. As you see, disturbance is traveling, but the particles or any object on the surface of the water will not displace. So waves move, yeah, or disturbance travels from one point to another, but water, any particles, medium is not displacing. It is not carried with the wave. So a medium stays in place and particles of the medium only vibrates up, down, back, forth. And if it is water on the surface, it draws the circle and continuously repeats. It makes a periodic motion, continuously moving a circular path. But this object will not move from one point to another. So then we can say that as wave passes, for example, assume that there is a leaf on the surface of water. As you make a wave and the wave is traveling through the surface of water, this leaf will not displace. So the leaf undergoes no net displacement. So leaf will stay in its place, only moves back, forth, up, down, and stays where it is. That's why wave motion is just a traveling disturbance. It is not the displacement of the medium. Medium does not displace. Don't forget this in wave motion. If medium is displacing, it is not called a wave in physics. It's called a flow, like rivers. So water is displacing in river. So it's a flow. Or wind. Air molecules are displacing, so it is the flow of air. So it is not wave, and in wave motion, what the medium does not displace, only medium vibrates, or particle of the medium vibrates. And uh, a medium is not always needed for a wave motion. So some waves needs medium, mechanical waves they are called. Mechanical waves need a material, yani molecular medium. Like water waves needs water, sound waves need air, earthquake waves needs the soil, waves on a spring needs a spring. But some waves do not need a material medium, which are called electromagnetic waves. So light is an electromagnetic wave, so it can travel from sun to the earth without a medium. Radio waves, ultraviolet, infrared, which all these are called electromagnetic waves. Electromagnetic waves do not need a material medium to travel. Even they are slower in material medium. They don't like medium. So without medium, they are fastest. But mechanical waves are not like this. They need a medium to travel. So no medium, no mechanical wave. No water, no water waves. No air, no sound. Of course, no spring, no wave on the spring. So then we classify the waves into two groups according to where they travel: mechanical waves and electromagnetic waves. And then we will now define the types of waves. The first one is the pulse wave. Pulse wave is just a small duration of wave like this. If you flip one end of the rope up and back again to where you are, so you make a pulse. So your hand will move up and back. So flipping one end of a taut means stretched rope, generates a pulse. A single traveling pulse, yani this pulse, is called pulse wave. It's called pulse wave. It's a traveling disturbance also. That's why if we say a wave, it's okay. Yani wave doesn't mean always one crest and one trough. Just one pulse is also can be said as a wave. But if you produce many pulses, how? Moving one end of a taut rope up and down repeatedly. So, repeated motion is called periodic motion. So you produce a periodic wave. So you are going to move your hand up and down continuously, repeatedly, and you are going to produce a periodic wave on this rope. This is called periodic wave. And every wave carries the property of its own source. So how many times your hand is vibrating up and down, so the particles of the wave is also vibrating up and down with the same frequency. Like in your book, this is an explained like a vibrating blade. It's a elastic object. So then when you attach a rope to this blade and then vibrate this blade up and down, this blade vibrating up and down produces a wave on the string. So this is uh, because blade is vibrating with simple harmonic motion. Vibration of each point on the string is also simple harmonic because blade is the source. So wave must have the same property of the source. So if blade is vibrating with simple harmonic motion up and down, so every point on this rope also will vibrate with simple harmonic motion. If a wave is vibrating with simple harmonic motion, that wave is called a sine wave. A wave whose source vibrates with simple harmonic motion is called a sine wave because its shape is exactly the same as a sine function. So this is the graph of a sine function. This is a sine wave. If you check this too, you will see that their shapes are the same, or they have the same figure. So that's why we say that if a source of a wave vibrates with simple harmonic motion, that wave will have a sine graph. It is called a sine wave. And then we will define the waves in terms of their direction of vibration and motion. So there are two types of waves. One of them is called transverse waves. Other one is called a longitudinal wave. In transverse waves, particles vibrate perpendicular to direction of wave motion, like this. So as you see, vibration is in vertical, but motion is in horizontal, which means the vibration and motion directions are perpendicular. So these types of waves are called transverse waves. All electromagnetic waves are transverse, but some waves are vibrating in the direction parallel to direction of wave motion, like this. As you see, particles are vibrating horizontal. Disturbance is also traveling in horizontal. So their direction of vibration and wave motion are parallel. So this is called longitudinal wave, and sound is a very good example for longitudinal waves. So then, according to direction of vibration and direction of motion, we classify waves into two groups: transverse waves, if the direction of vibration is perpendicular to direction of motion, so it is transverse. If direction of vibration and wave motion are parallel, it is longitudinal waves. And now we will define the transverse waves. First, we will talk about it because many waves around us is transverse. Electromagnetic waves is the basic transverse wave. So to study a wave, we should locate a wave on a coordinate system. So representing a wave in a coordinate system is called a waveform. So both transverse and longitudinal waves can be represented in coordinate system. First, we are going to represent a transverse wave in a coordinate system. So waveforms of transverse wave. Waveform that represents the displacement of each point on a wave at a single moment, which means this is a periodic wave in a string, and uh, the position of every different point is different when this picture is taken. So then if we locate this wave on this coordinate system, so this is the waveform of that wave. This is the waveform. So according to this waveform, displacement of the particles are in vertical. So these particles are vibrating in vertical, but wave motion is represented in horizontal. So wave is moving in horizontal, but particles are vibrating in vertical. And according to this waveform, we define the wave. So the 2 points, one point is highest point, other one is lowest point. The highest point above the equilibrium position, this is the equilibrium position. So above the equilibrium position, highest point, but just a point, it is called crest. This is one crest, this is another crest. But the lowest point below the equilibrium position, lowest point, this is the lowest point, another lowest point below the equilibrium position is called trough of this transverse wave. And next, we will define distances. Distances can be defined in horizontal and in vertical. In horizontal, so distance from crest to crest or trough to trough. It is called wavelength. Wavelength, length of a wave. So it is defined like this: distance between neighboring displacements. One crest, another neighboring crest. From one trough to a neighboring trough. So it is called one wavelength. The distance of the distance the wave travels during one cycle. So this is also wavelength. And in one cycle, this wave travels a distance which is equal to one wavelength. So that's why from here to there it is one cycle. One cycle. Half cycle, quarter cycle, one more quarter cycle, two quarter makes half, Half plus half is 1 cycle. That's why distance the wave travels during 1 cycle is called wavelength. This wave travels 1 wavelength, so in 1 cycle. And distance between two adjacent similar points of the wave, also from crest to crest, trough to trough, also called wavelength. So now here we have 3 definitions of wavelength. Distance between neighbor and displacements. Yes, neighbor. First, second. First, second. One after another, neighbor. So distance the wave travels during 1 cycle. It's also called 1 wavelength. This is distance traveled by when 1 cycle. Also distance between 2 adjacent similar points. Similar, adjacent, one after another similar points. Crest and crest, or trough and trough. So this is also wavelength. And second one is distance we define in vertical. Displacement of the particles, vibrating points from the equilibrium position. So maximum displacement from equilibrium position is called amplitude. So the distance from the equilibrium position to a crest or a trough is called amplitude. Equilibrium position, maximum displacement. This is 1 amplitude, or this is another amplitude, amplitude, amplitude. So you are going to measure distance from equilibrium position to crest, or from equilibrium position to trough. So they are called amplitude of this wave. And of course, this is all about the transverse waves, how we represent them on a coordinate system. But longitudinal waves are a little different, because longitudinal waves are vibrating in horizontal, also moving in horizontal, and direction of wave motion and direction of the vibration of the particles are parallel. So pumping a spring back and forth produces a longitudinal wave. So a wave whose particles vibrate parallel, which is back and forth, to direction of wave motion is called longitudinal wave. And pumping a spring back and forth produces compressed and stretched regions. When you pump forward, you compress it. When you pump back, you stretch it. So forward, compression, back, stretch. So there are regions of compression, regions of stretch, region of compression, region of stretch. So then the coils of the spring are tighter in some regions. As you see in these compressed regions, these coils are tighter or closer. These regions are compressed regions, and they have high pressure and high density. So that's why compressed regions are regions of high pressure and high density. But stretched regions, the coils of the springs are looser in some regions, here and here. These regions are called stretch regions, of course, because they are farther there. So then these regions are have low pressure and low density. Then we say that regions of low pressure and density, or regions of low pressure and density, are called stretch regions, and regions of high pressure and density is called compressed regions. And if we are able to draw a density graph along this longitudinal wave, so this is the a region of lowest density, lowest pressure. As you see, density is in vertical, and this is along the longitudinal wave. Lowest density is here. So as you see, I represent the density lowest. Compression, highest density. As you see, highest. Compression, highest density, highest. Stretch, lowest density. If we draw a graph, which is what this graph is called, density graph, or density wave or pressure wave, you will also see a sine graph. This is also a sine graph. This waveform represented by the curve is often called density wave or pressure wave. The compressed region, high pressure or density, corresponds to crest of this waveform, but stretch region is representing trough of this wave form. But this wave is completely different than the transverse wave, because in transverse wave, the vertical axis was displacement, but in longitudinal wave, vertical axis is density or pressure. Even their shapes are very similar, but they are not the same things. And then we will continue defining the frequency and period, because frequency and periods are very similar definition in simple harmonic motion. So wave frequency is defined as, first we should know that uh, source and wave will have the same property. For example, the vibration of vocal cords or a guitar string or a drum hat starts a sound wave. So these vocal cords, guitar string or drum hat, all they are sources. So produced sound is the wave produced by the source. So vibration of the source is transferred to the particles of the medium. So source is vibrating, and then this vibration is transferred to the air and makes the sound or makes the wave. The frequency of the source determines or is equal to frequency of the wave. How many times the source is vibrating in 1 second, so all the wave also will vibrate with the same number in 1 second. That's why frequency of the wave and frequency of the source always equal to each other. And wave frequency describes, this definition is a little different than the simple harmonic motion. So wave frequency is defined as number of crests or troughs that passes a given point in 1 second. So you are going to count number of crests or number of troughs. If you divide them in total time, so you will get frequency of the wave. For example, 12 crests passes a given point every 6 seconds. So frequency of the wave is what? So 12 over 6, which is 2 hertz. Wave frequency also describes the number of waves that passes a given point in a unit time, because when one crest passes to the next crest, it is one wave. From one trough to the next trough, it is also representing one wave. Number of wave that passes a given point, or number of crest or trough that passes a given point. This is the definition of wave frequency. And also we can define the period. Very similar definitions, again, very similar. Period of a wave is the time required for one complete vibration of the particles. One complete cycle, time for one complete cycle, or one complete vibration of the particles. So particle will start equilibrium position, go to the positive, to equilibrium, go to the negative, and back to the again here. It's called one cycle. So that time is called one period. And also period defined as the time it takes for one complete wave to pass a given point, because one complete wave corresponds to one cycle. So time for one cycle is period. Also, it is the time for one complete wave to pass a given point. Sometimes total time can be given, number of cycles and crests and troughs can be given. So you can also calculate period as total time divided by number of crests or troughs that passes a given point. And period of a wave inversely related to frequency. We know this from the simple harmonic motion. T is equal to 1 over F, or F is equal to 1 over T. For example, if you shook the end of a rope up and down 3 times each second, what would be the period of the wave set up in the rope? What would be the frequency? 3 times each second up and down means 3 cycles. 3 cycles in 1 second. So number of cycles in 1 second is called frequency. Frequency of this wave is 3. But period is 1 over 3. So total time, which is 1 second, number of cycles is 3. 1 over 3 is the period of this wave. And then we will define speed of a wave. Speed of wave depends on what? Speed of a mechanical wave is constant at a given medium at the same conditions, which means speed of a wave is changing only with the medium. For example, speed of the sound in air is 343 meters per second at 20 degrees Celsius. And speed of the sound in seawater is 1531 meters per second in 20 degrees Celsius. Temperatures are the same, both are sound, both are the same type of waves, but speeds are different. Why? One of them is air, the other one is water. So from medium to medium, so as you see, speed of a wave changes. Only the type of the medium or some properties of the medium, such as temperature, determines the speed of a mechanical wave. So then we can say that speed of a mechanical wave only changes when wave moves from one medium to another, from air to water, from air to rock, from air to a conductor or a metal. So it can change. Or you can change some certain properties of the medium, such as temperature. For example, cold air, hot air. In cold air, speed of a wave is small, but in a hot air, speed of a wave is greater. So that's why two things can change the speed of a mechanical wave. One of them is type of the medium. Second one is property of the medium. By changing the properties, it's also possible to change the speed of a wave in a medium. And speed can be calculated by classical definition of a speed, which is delta x over delta t, displacement over time. We know that a wave displacement is one wavelength in a time interval delta t, which is equal to one period. Yani a wave travels one wavelength in one period. So that's why displacement is one wavelength, time is one period, wavelength divided by period is going to be the speed of the wave. Yani by dividing the wavelength by period, you can get the speed of the wave. But 1 over t is equal to frequency. This equation can be written in an alternative form. V is equal to lambda times f. So then speed of a wave can be calculated by lambda times f. But this equation doesn't say you speed of a wave depends on what. No, speed of a wave does not depend on lambda, does not depend on frequency. Speed of a wave only depends on medium. So if medium does not change, you cannot change speed. If speed is constant, lambda and f can change inversely. If frequency increases, lambda decreases. If frequency decreases, lambda increases. What about speed? Always constant in a specific medium. If you don't change the medium, you cannot change speed of a wave. Then we say that um, because speed of a wave is constant in a given medium, v is constant. As a mechanical wave's frequency increases, wavelength must decrease by the same factor. Ne demek bu? If frequency doubles, wavelength decreases by 2. If frequency triples, wavelength decreases by 3. Or vice versa. If frequency is halved, wavelength doubles because speed is constant. Thus, frequency and wavelength of a wave inversely proportional in a given medium. If medium changes, of course there will be some changes, but we are talking about on a specific medium. V is constant, but f and lambda are inversely proportional. And speed of a wave is independent of wavelength and frequency in that medium. As I said, speed of a wave only changes with property of the medium, not with wavelength, not with frequency. And every wave carries energy. Waves transfer energy by transferring the vibrations rather than transferring the matter itself. So when, remember the earthquake 3 years ago here, so there was a crack maybe 60 kilometers away. But we felt the vibration, we felt the wave. This vibration is transferred from the center to everywhere, but we didn't see that Earth crust is moving. So that's why wave is a very efficient transfer, energy transfer method. So without, you don't need to transfer the medium, only vibration is needed to transfer from particle to particle. The rate at which a wave transfers energy is called power. The rate at which a wave transfers energy is called power. And this power or energy depends on amplitude of the uh, amplitude of the wave. If how changes with amplitude? For a mechanical wave, the transferred energy or power is proportional to square of wave's amplitude. Yani if amplitude is doubled, energy or power increases by 4. If amplitude is tripled, energy or power increases by 9. If amplitude is halved, energy or power decreases by 4. So then, when an amplitude is doubled, energy it carries in a given time interval increases by 4 because it is squared. When amplitude is halved, the energy decreases by a factor of 4. So as you see, that is squared. However, no wave can transfer all its energy infinitely because, of course, there is some air resistance, there is some friction. So, because over time energy of the wave is dissipated, amplitude gradually decreases, diminishes means decreases. Finally, this wave will stop. I mean, we are not going to feel that wave anymore because all its energy will be converted to other types of energy, especially to the heat. And this effect is called damping. Normally, we studied this in the second section when we are talking about the energy of a simple harmonic motion. And this is all about section 3. Any questions about section 3? I will continue with section 4. All right, I will continue with section 4, which is about the wave interactions, yani interference. First, we should know that two or more material objects cannot occupy the same space. As you see that two bumper boats cannot occupy the same space, but wave is not like this. Two or more waves can occupy the same space. So a person can hear the sounds of different instruments at a concert. How? Because wave from each sound can occupy the same space in your ear. This means many waves can occupy the same space at the same time. So if they can occupy at the same space at the same time, which they must interact with one another. If two or more waves passes through each other, they interact with one another. This interaction is called interference. Interference, in fact, in English meaning is meeting. So if two things meet each other unexpectedly, so it is called interference. So two waves meet each other, so it is called interference. As two or more waves overlap, which means meet, a resultant waveform is produced for an instant. Yani, these two waves makes a resultant wave, a third wave for a short time. This resultant waveform is the combination of two or more overlapping waves. If two waves meet each other, so it's going to be a combination of two waves. If three waves meet each other, it will be a combination of three waves. But in this section, we will only study two waves. This method of combining two or more overlapping waves is called superposition. So superposition is in fact a mathematical method used to add the vectors. So displacement is a vector quantity. So we add them and we find the resultant displacement. Superposition principle: when two or more waves meet in the same medium, displacement of the particles of the medium is the resultant, yani vector sum of individual displacement. So we are going to apply this now. For example, the first type of displacement interference we will study is constructive interference. If displacements are in the same direction, look at here, positive y and positive y. And if these waves are approaching to each other, so they are approaching each other, so then what will happen? They will meet. So like this one on the video, let's see that. So two waves approaching each other, as you see, when they meet, resultant wave, they for an instant they produce a resultant wave which is greater in amplitude. So they support each other, makes an amplitude which is greater, which is the sum of the amplitude of individual waves. Now I will stop when they meet. Okay, let's do it again. So they're approaching, and then now look at here. This is the amplitude of the first wave, which is 2 units. This is the amplitude of the second wave, 2 units. But the resultant wave is 2 plus 2, which is 4. So as you see, the amplitude of the resultant wave is the sum of the displacement of each individual waves. When you add y1 and y2, you are going to get the amplitude of the resultant wave. So the amplitude of the resultant wave is greater than amplitudes of the individual waves and equal the sum of the amplitude of each pulses. What if they are in the opposite direction? If their displacement, one displacement in positive phi, other displacement is in negative y. If displacement of the particles must be in opposite directions. In this case, so they will, of course, weaken each other. Let's see the video. So now two pulses approaching in opposite directions. For an instant, they cancel each other, but later they go on their own way. So then let's stop when they meet, when they overlap. So, sorry, I couldn't do it again. Let's try it. So they are approaching. Okay, so look at this point, So displacement, or let's take this point. So displacement of these 2 units up. What that one is 1 unit down. 2 minus 1 must be upward 1, as you see. So resultant part is 1 upward. So look at here for that point. The displacement of the first one is 2 units up. Second one is 0. So 2 minus 0, so resultant is 2 units up. And look at another point. Let's take another point. This is 1 up. That is almost 2 down. So 2 minus 1, it must be almost 1 down. So when you add it, subtract the displacement because they are in opposite direction, you are going to calculate the resultant displacement of the resultant wave. So if the amplitudes of the resultant wave is the difference between the pulses, so it is less than displacement of the wave of greater amplitude. So one wave is greater amplitude, the other one is smaller amplitude. Resultant will be less, absolutely less than the greater amplitude or greater component wave. This is the destructive interference. And after two pulses pass through each other, each pulse keeps its original shape and travel in the original direction. So when they meet, so only they form a resultant wave, but after that, so greater one amplitude wave goes to the right, smaller amplitude wave goes to the left. They travel their own wave without a changing. The same in constructive and destructive interference. But sometimes if two waves have equal displacements, when two waves pulses of equal amplitude but in opposite displacement coincide, the two waves completely cancel each other because their amplitudes are equal. So you are going to see that no disturbance at all. This situation is known as complete destructive interference. They will cancel completely each other. This superposition principle holds true for both mechanical waves and electromagnetic waves, which means you can apply, this interference not only for mechanical wave, it is also possible to apply them for light. We will study in chapter 7. So light can also interfere and produce a smaller amplitude, which is dark region, or greater amplitude, which is bright regions. And longitudinal waves also can interfere like sound. But in longitudinal wave, we have compressions, and which is compressed regions and stretch regions. If compression and stretch region overlap like crest and trough, so resultant will be 0. It's destructive interference. But if compression and compression, stretch region and stretch region interfere, so they will produce a constructive interference, as you see much. Okay, so we will continue with reflection of waves. First, we should know that if a wave is traveling from in one direction, for example, to the right, so the front of the wave, particles in front of the wave vibrates up, but the particles which is behind the wave is vibrating down. So the particles in front of the wave so will vibrate up, and the particles behind the wave will vibrate down. So when a pulse is vibrating towards a fixed boundary, so this rope is fixed on the wall, so how is the reflection? Or if this rope is not fixed on the wall, it's free to vibrate about a post, so then how could be the reflection? So we are going to now study these two cases. So if the first one is reflection of the waves at fixed boundary, a pulse traveling on a stretch rope that is fixed at one end. Here is the fixed, so this rope is not free to vibrate. Reflection of the wave at free boundary, a pulse is traveling on a stretch rope that is free at one end. As you see, there is a ring, and then this ring can move up and down freely. So we will study these two cases. First, so if a wave is a pulse is approaching to a fixed boundary, when the pulse reaches to the wall, so when this pulse reaches to the wall here, the rope exerts an upward force on the wall, because we know that the wall applies a downward force on the rope. This downward force, this reaction on the rope, causes this pulse to be direction opposite the displacement of the original pulse. So when original pulse is pulse vibrating in direction. What's the reason for this? As you see, it's approaching. So the reaction force causes the pulse to be inverted. This is from the fixed end, the direction from the fixed end, but the end is free. This end is free. When the pulse reaches the boundary, this free boundary, the rope is free to move. So this rope also free to move. If it's free to move, there will be no direction, there will be no direction of vibration. Then strings, the movement of the rope at this point is similar to the movement that would result if someone were to rip the rope up and send the pulse to the left. So because there is no direction, there will be no change in direction of vibration. If pulse coming vibrating by in positive y direction, after reflection, it will vibrate in positive y direction. And last section is standing waves. Consider a one end of the support. So we fixed both ends of the rope. If the string is vibrating at right frequency, the result wave pattern, which is called standing wave, the number along the string is produced. This is a point. So this red one, red is standing wave pattern, which only vibrates, seems to be not moving. It's not moving, but this is one wave is traveling to the right, other wave is traveling to the right. If you look at that blue, one wave is moving to the right, other wave is moving to the left. When these two waves form a resultant wave is called a standing wave. And for that reason, as the wave moving towards the fixed end and the waves reflected from the fixed end overlap and interfere constructively and destructively at different regions. This is a good animation about this. I'm going to show it to you now. Here is the waves are approaching. Because action force on one or reaction force on the wave. And from the it's will start reflecting. It will start to like here. From this start changing. So going turns down and then continues going to the back. But not from the start to the this will end because now structurally, it's more like now constructively, now structurally, and then structurally. So again, the tension is in the structure, the structure. And the structure is not structure. The structure is transfer. The thing is very this is complex. Now this is structure. And this will be only vibrating, but not. If current waves are moving, there are two waves. One of them is moving to right, which is red. Other one is moving to which is blue. But these two interfere, but the resultant wave pattern appears to be not moving. So standing wave is this. Basically, there are some things you should know about standing waves. First, The points at which two waves cancel are called nodes. So there are regions with zero displacement, this region, that region, that region. These points never vibrate. So those are called nodes. But some points are vibrating with the maximum amplitude. So midway between two nodes, there is a antinode. Midway between two adjacent nodes, the string vibrates with the largest amplitude. These points are called antinodes. And this is called one loop. One loop. That shape is called one loop. Sometimes like this, then going like this, down and not shifting. Continuously it is doing this up and down, up and down, up and down. So this is one loop. And number of antinodes and number of loops are equal. One antinode, one loops. Two loops, two antinodes. But number of nodes is one greater than number of antinodes. Now count. 1, 2, 3 nodes. But 1, 2 antinodes. That's why this is number of nodes. It's not antinodes. Number of nodes is number of antinode plus 1, or number of nodes equal to number of loops plus 1. And there can be different shape of standing waves on a string whose length is L. You can form this standing wave, which is called first order. This is called second order, 2 lobes. This is called third order, there are 3 lobes. This is called fourth order, there are 4 lobes. So these are the standing waves which can be formed on a string, pattern of standing waves. And you can calculate that these standing waves can be formed some specific frequencies and some specific wavelengths. If the length of the string is L, you can get at what wavelength you can produce a standing wave. For example, first order standing wave forms at what wavelength? You are going to write here 1 and 1, so lambda is going to be 2L. Second order standing wave forms at what frequency? So you are going to write here 2 and 2, 2L over 2, which is L. Third order standing wave forms at what frequency, wavelength? You are going to write here 3 and 3, so 2L over 3. Fourth order standing wave forms at what wavelength? 4 lambda 4 is equal to 2L over 4, which is lambda over L over 2. L over 2, yeah. So you can get possible